When we talk about quantum computing, it's easy to think it's just about making faster computers. But it's so much more than that. We're talking about a fundamental shift, a complete reimagining of what calculation even means. It's about tapping into the seriously weird rules of quantum mechanics to tackle problems that are flat out impossible for even the biggest supercomputers on the planet today. So let's dive right in.
I just love this quote from Charlie Bennett because it completely flips the script on how we think about this. It suggests that, hey, maybe the quantum world is the default setting for the universe, and our regular classical computers are the ones that are actually limited and slow. It's a great way to frame the question. What is it that makes these new machines so fundamentally different?
Well, the answer really boils down to this one thing, the qubit. Now, you know how a classical computer bit is stuck in its ways? It can be a 0 or it can be a 1. That's it. A qubit, on the other hand, can be a 0 and a 1 at the exact same time. It's this bizarre property called superposition, and it's the secret sauce that gives a quantum computer's almost unbelievable power.
And this is a fantastic way to picture it. Think of your regular computer bit like a light switch. It's either on or it's off. Simple. A qubit, though, is much more like a dimmer dial. It can be fully on, fully off, or, and this is the key part, it can be in any of an infinite number of positions in between. That ability to explore this huge landscape of possibilities all at once is exactly what unlocks its potential.
Okay, so qubits are clearly super powerful. But how do you actually build a machine out of them? Well, it turns out there's no single answer to that. Right now, the race to build a working quantum computer is actually heading down two pretty different roads. So here are the two main camps. On one side, you've got quantum annealing, with companies like D-Wave leading the charge. You can think of this as a specialist tool. It's designed to be amazing at one particular thing, solving incredibly complex optimization problems. On the other side, you've got the gate-based model, which is what giants like IBM and Google are working on. The goal here is the Holy Grail, a universal, do-anything quantum computer. And what's really cool is how differently they think. The annealing approach is kind of like setting up a complex landscape and then letting a ball roll downhill. Nature just finds the lowest point, the lowest energy state, which happens to be the best solution to your problem. The gate-based approach, on the other hand, feels a lot more familiar. It's more like a traditional computer, where you apply a sequence of logical operations, or gates, to the qubits to get your answer.
But here's the thing, it doesn't matter which of these paths you're on, because sooner or later you're going to run smack into the biggest, baddest roadblock in all of quantum computing, the problem of noise.
The fancy technical term for this is quantum decoherence. But here's what it really means. Qubits are, well, they're divas. They are unbelievably sensitive. The tiniest change in temperature, the smallest vibration, a single stray magnetic field, any of it can make a qubit lose its quantum magic. It just collapses from that state of 0 and 1 into a plain old classical bit, and your entire calculation is ruined.
And this is just the perfect way to picture it. A quantum state is just like a soap bubble. It's beautiful. It holds this incredibly complex world inside of it, but man, it is fragile. The outside world is constantly trying to pop it.
And we're not talking about a small problem here. The scale of this is, honestly, it's staggering. Right now, on today's best machines, you get about one error for every few hundred operations. Just think about that. Imagine if your laptop made a mistake every single time you typed a paragraph of an email. It'd be totally useless, right? For these machines to do anything meaningful, that error rate has to come way, way down.
So what's the plan? How do we fix this? Well, the solution is this incredibly clever idea called quantum error correction. The basic concept is kind of like this. Instead of relying on one fragile qubit, you take the information for that one perfect qubit and you spread it across a whole bunch of less perfect, real-world physical qubits. By doing that, you create a kind of team that can work together to form one super robust, logical qubit that can actually spot errors and fix them on the fly.
But, and this is a huge but, there's a catch. To pull off this real-time error correction, you need a staggering amount of classical computing power working alongside the quantum processor. We are talking about processing up to 100 terabytes of data per second. To put that into perspective for you, that is like asking a single machine to handle the entire global Netflix stream, every movie, every show, watched by everyone on the planet, and process it every single second. It is a mind-boggling engineering challenge.
So, let's just say we pull it off. We solve this monumental problem. You have to ask, why? What's the end game here?
What's the ultimate payoff for building these insanely complex machines? And that's where things get really interesting, because we get into both the promise and the peril of all this quantum power.
To put it as simply as possible, we're talking about the power to solve the unsolvable. We mean problems that are so ridiculously complex that even if you harnessed every single classical computer on Earth and let them run for the entire age of the universe, you still wouldn't get an answer.
And what kind of problems are we talking about? Well, the breakthroughs here could literally change the world. Simulating new molecules to create life-saving drugs. Designing revolutionary materials we can't even imagine yet. Building climate models that are actually accurate. Even revolutionizing things like fertilizer production, which, believe it or not, uses about 2% of the entire world's energy supply every year. The potential impact is just massive.
But there's always a but, isn't there? Every powerful new technology is a double-edged sword. And that same incredible power that could cure disease could just as easily be aimed at the very foundation of our modern digital world.
This isn't some vague hypothetical threat. It has a name, and it's been around since 1994. It's called Shor's algorithm, and it's a quantum algorithm designed to do one thing, and do it scarily well: break the encryption that keeps nearly everything we do online safe and private.
And this is where the rubber really meets the road. That public key cryptography that protects our online banking, our secure emails, our e-commerce, basically our entire digital lives, it's a sitting duck. A powerful quantum computer running Shor's algorithm wouldn't take millennia to crack it, it could take hours. Even the tougher symmetric encryption is still weakened.
And don't think for a second this is just a problem for tomorrow. The threat is happening right now. There's a phrase in the security community: harvest now, decrypt later. It means adversaries are stealing massive dumps of encrypted data today, and they're just sitting on it, waiting for the day they can switch on a quantum computer and unlock every single secret inside.
All right, so that brings us to the most important question of all. How do we build this amazing future without completely destroying the digital security of the present? The goal, the thing everyone is racing towards, is what's called a fault-tolerant quantum computer, one that has enough error correction built in to be genuinely useful and reliable.
And listen, this is not science fiction anymore. This is a concrete plan. Companies like IBM have public roadmaps. They're aiming to show off key error correction tech by 2025, see the first real examples of quantum advantage by 2026, and deliver the world's first truly fault-tolerant system by 2029. The race is definitely on, and it is moving fast.
So while one team is racing to build the quantum computer, another team is racing just as fast to build the quantum shield. The solution is called post-quantum cryptography, or PQC for short, and it's a whole new class of encryption that's being designed from the ground up to be safe from attacks by both classical and quantum computers. These new techniques are based on completely different kinds of math problems. They're using things built around complex geometric lattices and other really advanced math that we believe is just as hard for a quantum computer to solve as it is for a regular one. It's a whole new arms race, fought with mathematics. So here's the bottom line. The quantum revolution is no longer a question of if, it's just a question of when. It holds the incredible promise to help solve some of humanity's biggest problems, but it also carries the peril of completely upending our digital society. And the one question that leaves all of us with is, will we be ready for it?